Hi, George Crump, lead analyst with Steward, Switzerland. So how do you improve software-defined storage? Well, let's first talk about what software-defined storage is and how it works. So in a legacy system, a traditional storage system, you have an array. That array has a bunch of drives in it and has a storage controller in it. That controller provides you functions like volume management, snapshots, maybe replication, things like that. What software-defined storage does at a very simple level is abstract that controller out of the array and puts it somewhere else. It might be in the storage network. It might be running as a virtual machine up in a hypervisor. And by doing that, now I can support multiple vendors' storage systems. We think, though, that there's room for improvement. And I think the first step to improving software-defined storage is to do something called hyperconvergence, which is instead of having an isolated virtual machine that runs the software function, let's have that capability distributed across every node in the virtualization cluster. The advantage of doing that is it gives me some scale. As I add new hosts to the environment that's going to support more virtual machines, I'm also adding some percentage of additional storage controller processing power, so I can run more functions and still doing the snapshots and replication and things like that, but also do other things. So we think that's the first step. That creates sort of a scale out environment, meaning that I possibly don't need a shared storage system down here. And now I can put drives actually in the hosts. So we'll go ahead and draw those in, and so on. Now, obviously, what we do then with this software-defined storage component that's running in this hyper-converged storage environment is we then aggregate all of these internal drives and make them appear as if they're a shared drive. So it's a logical, not a physical shared capability. The advantage of doing that is now I can use low-cost enterprise-class server disks, which are less expensive than enterprise storage systems. And like I said before, now I can scale my environment pretty easily. But let's not stop there. Let's do more. The number two thing we think we can do, and this is done by companies like Atlantis Computing, is leverage the in-memory component in the server. We call that in-memory storage. So inside these servers, obviously we have RAM. Let's leverage that RAM to do a couple of things. First, let's leverage that RAM as a high-speed processing area to improve efficiency. Because I'm still, even in this hyper-converged environment, I'm still transferring data across the network. I'm still having to write to storage media, things like that. So the more efficient I am, the better performing the environment will be, and the better it will scale. So let's leverage RAM to do things like deduplication and compression. So before we put data out into our logical volume, we're minimizing the amount of data that has to be transmitted across the network and the amount of data that has to be stored on these systems. So that's kind of the first thing. The second, in addition to deduplication and compression, we can also leverage this RAM to do something called write coalescing. And that is, the basic theory behind write coalescing is that the same data tends to change a lot within a very short period of time, seconds. Write coalescing basically takes the last copy of that and only transmits that one. And so similar to deduplication and compression, it's very efficient and minimizes the amount of data we're sending across the network and writing to our storage layer. But we can go further and use that RAM to improve performance in a couple areas. First of all, we can use this additional RAM and aggregate it as well as a storage area. That storage area could be used for sort of a caching or high-speed tier, or it could even be a dedicated storage area that's RAM only. You might do this in sort of an analytics processing situation where keeping the data protected isn't super important, but processing it very quickly is. And so that would be the area there. And so we can leverage this to improve, we can leverage that RAM to also improve performance as well as improve efficiency. And then finally, let's also improve the cost per gigabyte. Now, in this environment, we might have three tiers of storage, right? Like I talked about before, we have this in-memory tier that is going to be used for very high-speed data. It's going to be used for caching, things like that. We might have flash, which sort of becomes an intermediary tier. That flash can be used as a high-speed storage area with obviously protection from a power failure or something like that. And then third, of course, we're probably going to still have hard drives. So if we have hard drives, that becomes our capacity tier. Well, we want to, in that area, in both of these areas, we want to still improve our price per gigabyte. So let's leverage the efficiency we used up here and provide deduplication and compression throughout all of these different storage tiers. So that way I'm using flash as efficiently as possible. Also, by the way, I'm writing to it less often. And then I'm also using the hard drive, even though those are already affordable on a price per gigabyte basis, using them more efficiently has a lot of value. Because remember, in these servers, since I'll be using local server storage, and I'll probably have some of that set up as flash, and then some set up as a hard drive, I don't have as much space, say, as I would in an enterprise class array. So that's the value there, is let's drive down the dollar per gigabyte as best as possible, and we can leverage a lot of the work we did up here. Now the key, though, for all this to function is really to leverage this memory up here, or RAM, what we'll call in-memory storage, to really take the software-defined storage concept to a whole new level that can do more than just eliminate shared storage. It can also improve efficiency, improve performance, as well as improve the price per gigabyte.